Okay. Hi, everyone. So we now have today Sven Heinemeyer, who I think most of you know anyway, but Sven is really a very big expert on precision Higgs calculations and also precision calculations in the Electroweak sector in general. He's one of the main authors of FeynHiggs, which is, well, it was already a famous code when I was a PhD student, and it remains a famous code. And also HiggsBounds, HiggsSignals, which I think is like this new code because it got developed after my PhD, but is now very mature and well known. And he's also a member of the MasterCode Global Fitting Collaboration, which is also famous. Yeah, he's a professor in Madrid, and he's been there since 2016. He actually did his PhD in Karlsruhe with Hollick. And he's held positions at DESY, Brookhaven, and CERN. Okay, so please go ahead, Sven.
Yes, hi, Peter. Hi, everybody. Thanks a lot for the invitation, which I'm very happy about, that I can talk to you about some of my favorite topics here. And as I was saying before, it would be so much nicer to be there in person, of course, yeah, to visit China, visit Nanjing, where I've never been. And I hope that this can be realized somewhere in the future. Now, coming to the talk. The talk title consists mainly in abbreviations. First order electric phase transition, triple Higgs couplings, and gravitational waves in the 2HDM. And after some introduction, I will indeed talk about first order electric phase transition and gravitational waves in the 2HDM, and I'll try to make this connection. And then the second main part, the triple Higgs couplings at the HL-LHC, and a little bit also at the e+e-colliders. I put here ILC because we need higher energies than what could be done, for example, at CEPC. But actually, I'll focus mostly on the HL-LHC here. And if time permits, I will show you my first neural network analysis, which is closely related to this topic here, where I myself thought that in my work, I don't really need neural networks, but then this specific application proved so accessible to neural networks, and I think the results are really fascinating. Let's see whether we get to this. Good, let's get started. Introduction. I want to combine two Nobel Prizes. It's always nice to combine Nobel Prizes, and we know them, of course, the one for the Higgs and the one for gravitational waves that was awarded 4 years afterwards. And you may ask, what is the connection between these two? Can there be a connection? And interestingly, the answer is yes, there can be a connection. And it starts out with a question, why is there more matter than antimatter in the universe? And one of the top candidates, one of the two candidates that is really analyzed in the literature is called Electroweak baryogenesis. And I will not talk about electroweak baryogenesis. It's just something that can take place in the very early universe. And it requires three conditions, the famous three Sakharov conditions. And one of them is an out of equilibrium state that is needed for some time. And this can be realized indeed if one has a first order electric phase transition, or even to be more concrete, a strong first order electric phase transition. And this can happen in principle in the early universe when we get to the right vacuum where we are sitting now with the VEF and the Higgs potential. But we know that the first order electric phase transition is not possible in the standard model, where we have not even a second order electric phase transition, but more like a crossover, which is even smoother than a second order phase transition. So in the standard model, this doesn't work, which means we need a BSM Higgs sector. Yeah. So the question that we want to explain more matter than antimatter naturally leads to extended Higgs sectors. Now, we can analyze the Higgs sectors, and then one finds that, I'll come to this in more detail, that as a bonus, this first order electric phase transition can also cause gravitational waves that may be detectable with LISA or other space-based observatories. I'll come back to this in a moment, but LISA is the one that is actually approved already. I'll show you how this works in a moment. So let's first take one step back and see what can happen as the first order electric phase transition or second order let's start with the right-hand side, which is more closely to what will happen in the standard model. We start out at higher energies with our potential, and we are sitting here at the minimum. We're always living where the little black ball is located. The universe cools down, we go down in energy, and then here a second minimum starts to form. You can see that the vacuum state where we are smoothly goes over here, and then we have this minimum, and we are sitting at this VEF. The distance here is the VEF, and this is where we are right now at 0 energy, and we are sitting here. Everything is smooth. This is what more or less would happen in the standard model, and there's no first-order electric phase transition. So this doesn't help us. On the other hand, on the left side is what we want, the situation that we want, and this can be realized in BSM Higgs sectors. We start out with the same potential here, and then the second minimum starts to form, but there's this barrier here that forms, and at some temperature TC, these two minima have the same depth. So at that moment, in principle, the phase transition is possible, and shortly afterwards, at the temperature Tn, we can tunnel through, and this is then where the first order electric phase transition takes place. We tunnel through, we have this out of equilibrium condition, and then we are living in this vacuum here. I will make the distinction between TC and Tn several times later. You will see this. Yeah, but TC is where they are equal, and Tn is where actually the tunneling takes place. As I said, a BSM Higgs sector is required to realize the first order electric phase transition. Now, what happens in that moment when we have this this tunneling through? How can we picture this? What happens is that at several places in the universe, here or here, we tunnel through, and then the space where we are in the real vacuum with the VEF non-equal to 0 expands nearly the speed of light and forms these bubbles. And on the surface of these bubbles, this is where we have this non-equilibrium conditions, and then electric baryogenesis can take place. And if this phase transition is strong, then the creation of matter over antimatter cannot be washed out anymore. This is why we need to have a strong transition here. The stronger in principle, the better, but we'll come back to this. Yeah. So here the VEF is already good. Here the VEF is still 0. They expand. Now, also this bubble expansion can cause these gravitational waves that may still be observable with the observatories that we will have in the future. Yeah, this is this bubble expansion, and also the turbulence that exists here in the plasma that we have. Yeah, this all causes gravitational waves. And to visualize this, I also took this picture here from NASA. So LISA is the only approved space-based observatory. It would be put here in, I think, the second Lagrange point, consists of 3 satellites, all 2.5 million kilometers apart. They send lasers back and forth. It's like LIGO, Virgo, Kagra, just much bigger and in space. And if some gravitational wave is emitted, we hope to see this with a space-based observatory. Yeah, the approved launch date is the mid-30s, so in a bit more than 10 years from now. This is the general idea, and this is how these two Nobel Prizes can be connected to each other. Now, coming to the playground where we will analyze all this, we work in this talk here in the Two Higgs Doublet Model, where we extend the Higgs sector of the standard model by a second doublet shown here. And then the potential looks a bit more complicated because we can combine 2 doublets. After electric symmetry breaking, out of these 8 degrees of freedom, 5 remain as physical Higgs bosons: light, heavy, CP even, CP odd, and a pair of charged Higgs bosons. And the input parameters that we are normally using are depicted here. We take all the masses as free parameters. Then we have one parameter that softly breaks in Z2 symmetry. I'll come back to this in the next slide, which is called M12. You can see this here, this parameter. And we have the standard model. Well, we have the VEF, the V, which is the square root of V1 squared plus V2 squared, which has to correspond to the VEF in the standard model to give the correct masses to the W and the Z bosons. As the second parameter describing the 2 VEFs that we have here, V1 and V2, is 10 beta, which is V2 divided by V1. And finally, we have another angle, the angle alpha, that diagonalizes the CP even Higgs sector, and then a parameter that allows us to easily handle the parameter space is cosine beta minus alpha. We will see why this is a good parameter for the model. Yeah, particularly if we want that the light Higgs in the spectrum, this one here, behaves like the standard model Higgs boson. We want to be close to the standard model Higgs boson. We can go to the so-called alignment limit. We can set the mass to 125 GeV because it's a free parameter. And then having this angle cosine beta minus alpha going to 0 gives us that all the couplings of the light Higgs are identical to the Higgs in the standard model. And then it also naturally agrees with the measurement of that we have at the LHC, where we know that the Higgs boson observed there behaves within 10% or so like predicted in the standard model. Interestingly, in this model, we not only have one triple Higgs coupling like in the standard model, but we have many more of them depicted here, and particularly this one, 2 light, 1 heavy, CP even Higgs. This will play a major role in what I will tell you later on. Okay, this is the playground. And a little bit more on the details. I said we have a Z2 symmetry, which is introduced to avoid flavor change in neutral currents. And this is how it acts. And as I told you, this parameter M12 breaks this symmetry softly. And the extension of the Z2 symmetry to the fermions gives us 4 fermion types, which are quite well known in the literature, 1, 2, 3, 4. And they are determined by the doublet to which then one of the fermion types is allowed to couple. And we will mostly work in type 1 and type 2. Type 2 is the famous SUSY type, and type 1 is the one where all fermions couple only to one of the 2 doublets. If we go to the alignment limit, then as said, we have this cosine beta minus alpha equal to 0, and then the sign must be close to 1. We know this. Adding this with other constraints like unitarity and perturbativity, electroprecision data, we know that the heavy Higgs bosons can't be too far apart in mass. They are not identical, but they can't be too far apart. Good. Now, as I said, we want to understand, we want to know whether we can have in the Two Higgs doublet model the situation of a first order electric phase transition, and maybe can we observe gravitational waves there. And in order to analyze this, what do? Well, you do a smart parameter scan and analyze your parameter space. In magenta, I always indicated the codes that were used to perform this part of the task. And in the parameter space, we first fixed a few parameters, 10 beta 3, we go to the alignment limit, and we fix the M12 squared to the heavy CP even Higgs mass with the 10 beta here. This helps us with some of the constraints. Furthermore, we set these two equal, again, to satisfy some of the constraints, which leaves us with 2 free parameters, MH and MA. And these parameter choices have been done in such a way that we know already this favors, for example, first order electric phase transitions. And we will see this in the results in a moment. But this is not all. We have to take care that all theoretical and experimental constraints are actually fulfilled. And I list them here, all the constraints. We require tree-level perturbativity, we require that the minimum of the potential, that we live either in the minimum of the potential, or at least that the minimum is sufficiently long-lived, that the lifetime is larger than the age of the universe. We take into account that all the additional Higgs bosons that we have in the model are in agreement with the searches at Lab, Tevatron, and the LHC, where we use our own code HiggsBounds. We also require that the Higgs at 125 is in agreement with the measurements at the LHC. I don't say that it is that it must behave like the standard model Higgs, but it must be in agreement. And then we use our own code HiggsSignals, which gives you a chi-square taking into account all the measurements that have been performed at the LHC. Flavor physics can be important, and mainly the charged Higgs sector enters through these 2 observables, and we require that these are also okay. And finally, electric precision data, mainly incorporated here via the S and T parameter, the Peskin-Takeuchi parameters are also taken into account. So these are all the constraints. And I'd like to mention that we include, of course, higher order corrections to the triple Higgs couplings, which will be crucial for the evaluation of the Higgs potential. We include higher order corrections at t equal to 0, and we include temperature-dependent corrections, but I'll not go into details there, where we use the code BSM-PT to evaluate here the one-loop corrections, particularly to the lambda triple Higgs coupling of the H125. Good, so this is our setup, and now we look at the results of this parameter scan, which is shown here. As I said, we have two free parameters, MH and MA, and then we get all these points. These points up here and up here are disallowed by some of the constraints. But we have even more restrictions here. The dark gray is where the global minimum of the potential is still in the origin. So this is not viable for us. And then we show as the color coding the quantity called Xi-C, which is the VEF at the temperature Tc divided by the temperature Tc. And remember, Tc is the temperature where the two minima have the same depth. And often in the literature, it was said that, yes, if we have a Tc that is larger than 1, this indicates that we have a strong first-order electroweak phase transition. So the color coding tells you the value of the Xi-C, where light gray is Xi-C smaller than 1, but the nicely colored area here gives us the Xi-C larger than 1, and this was the area where people before in the literature thought this is where we have strong first-order electric phase transition. And then the question is, can this result also in a strong gravitational wave signal? However, there's one more line in the plot, and this is very important, which is the black dashed line, which is close to this colored area where Xi-C is larger than 1, but not really the same area. And this is actually where the transition to the new vacuum takes place, meaning at a slightly lower temperature Tn that I indicated before, this transition actually takes place. But what happens in this area outside here, where actually the Xi-C was largest? This is where the distance in field space between the two vacua is so large that despite the fact that the second minimum is deeper, no transition takes place. Yeah, the tunneling probability is so small that no transition takes place. And one can see that the points with the largest Xi-C, where the strongest phase transition and the strongest gravitational wave signal was expected, is actually excluded by the requirement that the transition actually takes place. And this is the area that we like to call vacuum trapping. Yeah, we are trapped, or the universe is trapped in the wrong vacuum, in the vacuum at the origin, and it can't tunnel through to the deeper minimum, and we don't have this electric phase transition, neither strong nor weak. And this leaves us with this area inside the black dashed line, where, as I said, the phase transition actually takes place. Now, in a bit more detail, this is one of the nicest plots, I think, that we have here. We show again the same parameter space, but now we show 6 different areas, and I call this, there are possible 6 thermal histories in the 2HDM. Where this zone E is the one that was indicated here. This is the zone E, now called zone E. And now the color coding actually shows you Tn, which is the VEF at the temperature Tn divided by Tn. So here actually the tunneling takes place. The smaller Tn, the better is, or the stronger is the phase transition, and the stronger is also the potential gravitational wave signal. And one can see that indeed here the yellowish colors, they are located here very close to the zone D. And D is the one where we have this phenomenon of vacuum trapping, where no phase transition takes place. So we have a weaker phase transition here, a stronger here, and then it would be even stronger, but then we are so far away in field space that transition does not take place. And then we have all these other thermal histories here. Maybe I show this on the next slide. This is again these 6 zones, A, B, C, D, E, F. And again, E is the one that we want. We start out at high temperature in the universe, we cool down, and the orange and the blue lines show you the minima that we have in the potential. So we go, and black dashed is where we actually live. So we come here, and then at some moment, the second minimum starts to form. And then at this red dashed line, we tunnel through, we go up here, and then we continue here living in the minimum. And this V here is the VEF that we know from the standard model. So this is exactly what we want with this strong phase transition. We have also this vacuum trapping phenomena, which is shown here. We start out at high temperature, and then the second minimum starts to form, but it's already so far away in field space that we don't tunnel through. We keep living here. There's the second minimum. It's the deeper one indicated by this little box here, but we never tunnel through. This is vacuum trapping. Or more the standard model case, we start out here, and then the minimum just goes over, and this is a more smoother transition. And then there are other thermal histories. I will not go into details here. These are maybe the most relevant ones, and only the zone E is then the viable one where we have the strong first order electric phase transition. So zone E is preferred by phenomenology. Now, I told you that this can cause gravitational waves that may be detectable with LISA, and we took here one point. Actually, this is the best point that we found in our sample, which is still allowed. And this point via the bubble expansion causes the gravitational wave spectrum indicated here. And then the different colors tell you which bubble wall velocity we have chosen. Yeah? The bubbles expand with nearly the speed of light. One would be speed of light here. But the problem is that we can't really calculate the bubble wall velocity. There are ideas how to do this. People are trying to do this, but there's no real method worked out. Therefore, we put this here for several bubble wall velocities, and you can see that the spectrum differs always. Yeah, it can be higher or lower. And the dashed line is when also the turbulences in the plasma is taken into account. So this is more realistic. Let's take, for example, here the W equal to 0.6, which is actually the strongest signal, starts here, the dashed line equal to the solid line, and then here we have this dashed line, which gives you the more realistic spectrum. Now, this line here is the LISA line, the sensitivity line, which is a line given by the collaboration, and you may think, we don't touch, so there will be no gravitational wave signal. This is a wrong conception, because the so-called signal to noise ratio detectable at LISA is shown in this little equation here. This is the time of the LISA running time, so to say. And then what one does is one takes the integral over f, the ratio of the gravitational wave signal divided by the sensitivity curve. Yeah? So this here divided by this, and then the integral. And if this signal to noise ratio is larger than 1, or even better, larger than 10, one can talk about the detection at LISA. I'll show you the values of this in a moment. But this is the equation to calculate the signal to noise ratio. And it's not necessary actually that these two curves intersect each other. Of course, the higher this curve below, the larger this ratio, the larger the signal to noise ratio. Now, how does it look like? We did a scan over the relevant parameter space, which is actually, I will show this, the scan that we did is the one in this very strip here, yeah, where we are close. This is where we do the parameter scan. And then the result of this addition of this new parameter scan is shown in this plot. The x-axis is delta m, meaning ma minus mh, the difference between our two free parameters. The color coding tells you the value of mh. And on the y-axis, we have the signal to noise ratio evaluated for the most favorable bubble wall velocity, 0.6, and the anticipated lifetime of LISA, which is 7 years. So we calculated the signal to noise ratio. This is the one line. And one can see that in this parameter scan, several lines are below 1, but sometimes we are above 1, we are above 10. Some points are even above 100, which would give us the strong gravitational wave signal. On the other hand, the area where we would expect it the strongest one is exactly where this vacuum trapping takes place. Yeah, as one could anticipate from the first plot that I've shown to you, the darkest colors or the brightest colors are in the zone that is later forbidden by vacuum trapping. So the largest gravitational wave signal that originally was anticipated, we showed that actually there is no gravitational wave signal because it's forbidden by vacuum trapping. And it's only a small zone in the parameter space that actually gives you this detectable gravitational wave signal. Good. Now, this is a different way to show the results. And here I introduced the parameter kappa lambda, which is the ratio between the lambda value, the triple Higgs coupling in our model, divided by the standard model value at tree level. This is just another way to conveniently show the results. And now the results are shown. It's the same parameter scan as before. in the plane of the mass difference, MA minus MH, versus kappa lambda. And then we find all these points. And again, you can identify these 6 zones, A, B, C, D, E, F. Yeah, exactly the 6 zones that we've seen before. And one can see that the zone E that we are interested in is between roughly 1.5 and 2, a little bit over 2 here. So we need large kappa lambda values, large deviations from the standard model value here, which are caused in our case by higher order corrections. I'll come back to this later, that we can get these larger values. This line is the current line, the current limit coming from Atlas. CMS has a similar limit at 6.3. This is the upper limit that can be reached at the HL-LHC, provided that kappa lambda is equal to 1, that the standard model value is realized. And this would be the limit that could be reached at a plus and minus machine with 500 GeV center of mass energy, where concretely we took the numbers from the ILC 500. If you're at lower energies, only 250 or 350 energy, the precision that you get is much worse. It's more closely to this 2.3 line here. Okay, so this is the zone that is preferred, and it requires that the kappa lambda is a little bit smaller than 2, and that we have this large mass gap of around 200 GeV. These are the 2 characteristics that one can find. Coming back to gravitational waves, on the right-hand side, we also depict the zone where the signal-to-noise ratio is larger than 1. This is this pinkish zone here, and there we really need kappa lambda equal or close to 2, and again, this mass gap 200 GeV or a little bit larger. Very good. So these are the findings. If we want to live, if we live in the 2HDM and we have this first order phase transition to explain the matter-antimatter symmetry, then naturally we have this kappa lambda in the regime of 2 and this large mass gap. These are the 2 predictions that the model makes. Now, what does this imply for us? It implies that particularly this decay here, I hope you can see this well, this decay would be a very interesting channel, and it was called, not by us, but by people who looked at this previously, the smoking gun signature in this model. Because of this large mass gap, we can have the production of a CP Higgs, and then the CP Higgs, because of the large mass gap, can decay to Z and the capital H, and because we are at low 10 beta, the capital H mainly decays to TT bar. So this is the state that we're looking at, A to ZH to Z to TT bar, and the Z would go to L plus L minus. And in the parameter space, where now with the color coding tells you the Xi-n, this is where this smoking gun signature can take place. And we put here the projections that we had originally in early 22. We put projections out what could be covered at the various stages of the HL-LHC. And this is the area that potentially could be covered with all the HL-LHC data. And one can see that all the relevant part of the parameter space can potentially be covered. The one where we would expect also gravitational wave signal. Then some interesting thing happened in 2023. Atlas put out the first search result in this channel. Yeah, they looked at this channel. Now they have here the plane MA versus MH, and look at the results for 10 beta equal to 2. This is the expected area. This is the observed exclusion, and they don't really agree with each other. They don't agree because over here, Atlas observed an axis of events, nearly 3 sigma axis of events, which for us was very interesting, was in the right spot. It had more or less these masses that is really, I'll show to you, in the zone that we were interested in. Yeah, this is again our parameter space, the zone E. Color coding is the Xi-n, and this is where the axis was observed. This is the point with the highest local axis of nearly 2.9 sigma here. These colored areas are excluded by one or the other constraint. I will not go into details, but the red one here is indeed the search by Atlas. This was the expected exclusion. The solid one is the observed exclusion, and this is where the axis is located. It's right in the sweet spot. And then comes the spoiler. CMS did a similar analysis very recently, a few weeks ago, and they couldn't confirm this axis. Yeah? Therefore, I will not go into two more details here. We had really some hopes that the CMS would also see something, but as it usually happens, normally happens in nearly all of the cases, one experiment does not confirm the other. But to finish this up, potentially, because I mean, it means that now here this may be excluded, but the other area is of course still allowed. So in principle, the whole thing is still allowed, just not with this axis that Atlas had observed. What about the potential gravitational wave signal? Now, this is what we did those days. We took the point of the highest axis. The mass determination is not very precise, so we looked at a circle of plus minus 50 GeV around this, the masses. And then this is our zone E, which we populated with our parameter scan. This is the expected Atlas exclusion, this is the observed Atlas exclusion, and the color coding now tells you the signal to noise ratio. And one can see that if this point, the original point of Atlas, was realized, we would have a very low signal to noise ratio, nothing observed at LISA. We would have to be lucky to sit really in this small zone up here where we got a large signal to noise ratio, something could be observed. So we phrased it like this: the gravitational wave signal at LISA is possible, but by no means guaranteed. It's more the opposite, that we would have to be lucky to observe something here. Good. So much for the gravitational wave complementarity with the first order electric phase transition. Now let's focus more on the second part of the talk, on the trilinear Higgs couplings and possible determinations at high luminosity LHC and a little bit also at the ILC. And this plot here is quite famous. It compares all the collider options in their precision of the trilinear Higgs coupling. They call it now kappa 3. This is our lambda, little h, little h, little h. And as I said, we use, oh no, sorry. Their kappa 3 is this kappa lambda that we also introduced here. Yeah, this is this kappa lambda. And they say, it's very well known, that the kappa lambda determination at the high luminosity LHC is at the level of 50%. Yeah, this is what we expect. And then there are these light dash curves, which are obtained at colliders where we don't have access to di-Higgs production, but only single Higgs production. And then the trilinear Higgs coupling enters only via loop corrections. And one can see, depending on where we are, that the improvement over the high luminosity LHC is moderate or even non-existent. Yeah, we often stay here at the 50% line. The solid bars, they indicate colliders where the where we have access to the di-Higgs production because the center of mass energy is high enough. For the E+ and minus colliders, this is the ILC and CLIC, the linear ones, where we can actually go to higher energies. Or here, if FCCHH would do the job, then we could also go to a better determination of the trilinear Higgs coupling. But I will focus here on the high luminosity LHC and the ILC, where at 500 GeV we would get something like 25% determination. If, and now the two BSM Higgs cases come to the game, this evaluation here assumes that, first of all, kappa lambda is equal to 1. It only focuses on the standard model value of kappa lambda. And it also assumes that no BSM triple Higgs couplings are in the game. Yeah, this is all neglected. So this is a very simplified analysis in this respect. And I will tell you something about these two BSM cases and how they can modify the picture. Now, first, a few words about di-Higgs production at the LHC. This is what we can do and we'll access in the upcoming next 10, 15 years. Let's look at these two diagrams here. This is the signal diagram where we have here the light Higgs that then decays to two Higgses, and the triple Higgs coupling enters exactly here. The Higgs is produced via a top triangle coming from two gluons. And there's a background diagram where the two gluons produce a top quark box, and then this box radiates 2 times the Higgs. And of course, we have to sum them up, and there is a destructive interference between the two. And this results in the fact that the cross-section that we have in the di-Higgs production is much lower than, for example, single Higgs production because of this destructive interference. And this is shown in this plot. This is the cross-section as a function of kappa lambda. Kappa lambda 1 is the standard model, so we live, this is the gray curve, is the result, we live here. And if we make kappa lambda larger, the cross-section goes down because the interference between these two diagrams is destructive, as I said. And only at very large values, 3, 4 or so, it goes up again. And then the cross-section grows. This is what happens in standard model-like cases with varying kappa lambda here at the high LHC or high luminosity LHC. And as I was telling to you, we also take into account higher order corrections. In the 2 Higgs doublet model, we take into account the higher order corrections, which can be much larger than in the standard model. We take them to account as corrections to this vertex here. And you can see this depicted like this. What gives the main effect here are the corrections coming from the heavy Higgs bosons, because we have now here new triple Higgs couplings in the game that are not present in the standard model, namely the triple Higgs coupling between one light and two heavy ones. These can be large, and they can give very large corrections that result, for example, in the fact that our kappa lambda value is 2, 3, or even higher in the scan that I've shown to you. Yeah, they come from this kind of corrections. Now, take into account only this type of corrections, of course, neglects some other corrections, and those are depicted on the right-hand side, which would be corrections to the box, yeah, to this diagram here. And one can do a power counting. Here we take into account triple Higgs coupling cubed, whereas here we have triple Higgs coupling cubed and one additional Topukawa coupling. So these are included in our analysis. These are not included. And two remarks are in order. First of all, what we take into account is always a closed subset. Yeah, the ones with the triple Higgs couplings cubed only enter in this kind of diagram, so it's a closed subset. One can consistently include them in evaluation. And if these couplings are larger than the Topukawa coupling, then they're even the dominant ones. Yeah, so it can be, and we are often in this part of parameter space where the corrections that we take into account are the dominant ones. So we do a good approximation. A full calculation would be desirable, but it's not really available in the 2HDM where all these corrections are taken into account. Yeah, we can't do this technically right now. Good, so this is what we are doing. We do the calculation of the Higgs production, taking into account this kind of corrections. Just to mention this, the triple Higgs production, the di-Higgs production is also possible at the plus and minus colliders. And then we have this kind of diagram where the Higgs is radiated from the Z and then decays to two Higgs bosons, or at higher energies, the weak boson fusion channel. And of course, there are also these background diagrams where the two Higgses are not radiated from the triple Higgs vertex, but are radiated directly from the Z boson. Now, this is the behavior, how it's in for the, let's focus on the ZHH channel, the one that I've shown to you on the previous slide. And this delta kappa lambda is the deviation from the standard model value. And now the interference between this diagram and the diagrams where the Higgses are radiated directly from the Z is constructive, meaning we go to positive values here, we go to higher values of kappa lambda, and the cross-section actually increases, contrary to the high luminosity LHC, where it decreases. And this will be important in a moment. Now, what about the determination of the triple Higgs coupling at high luminosity LHC versus ILC in the cases where the kappa lambda is not equal to 1, so going beyond the original plot that I've shown to you where all these colliders have been compared. And this is shown on this slide, where now kappa lambda ranges from -0.5 to 2, where we are interested in this zone mainly. The black lines indicate the high luminosity LHC precisions, where 1 is the one that we've seen, the 50% determination. And then these others are extrapolated coming from the size of the cross-section that conserve. And remember, the cross-section goes down, meaning the precision in kappa lambda also goes down. This is why these bars become larger. Green is the determination at the ILC 500, and one can see that here we profit from the fact that the cross-section goes up and the relative uncertainty actually goes down. Red would be ILC 500 plus 1 TeV, where we get to even smaller uncertainties over here, but let's focus on the green lines here. Remember, the requirement of a first-order electric phase transition gives us that the kappa lambda is around 2, a little bit smaller than 2, which is, as you can see here, bad for the high luminosity LHC, but good for the ILC. And this is shown on this slide here. Left-hand side, high luminosity LHC, right side, ILC 500. This parameter scan that we did for the area where we find the strong gravitational wave signal. The signal-to-noise ratio is now on the x-axis and kappa lambda is on the y-axis. And the color coding tells you the precision with which kappa lambda can be determined. And one can see that in the zone of interest, signal-to-noise ratio larger than 1, that the high luminosity LHC, the precision degrades to 70, 72, 73%. Whereas for the ILC 500, where originally for kappa lambda equal to 1, we had a precision of 23% or so. Now we find a precision at around 10%. Yeah. So the precision improves substantially in the zone of interest that is favored by the first order electric phase transition and the gravitational wave signal. So this is some bad news for the high luminosity LHC and some good news for the plus and minus collider operating at 500 GeV center of mass energy. Good. But now we come to the second BSM topic, the second BSM case that I want to make, where also this diagram here plays a role, where we first produce a heavy Higgs in the resonance, and this can be indeed resonant if the mass is larger than 2 times the light Higgs bosons here, and then a second triple Higgs coupling comes in again. It's the first time that a second triple Higgs coupling becomes important, the coupling of 2 light and 1 heavy Higgs boson here. Yeah, so far all analyses that we performed dealt only with this triple Higgs coupling, and now we do a step further. We now take into account also this BSM triple Higgs coupling. And let me make some more remarks here. The experimental collaborations, ATLAS and CMS, they search for di-Higgs production, and they make the distinction between 2 cases. Either non-resonant production, this diagram here, they look for this, but they only take into account this diagram. They neglect these 2 diagrams in their evaluations. They don't look at them, they don't take them into account in the calculation, in the templates they're forming. They only have the signal diagram here. Or, sorry, they look at the pure non-resonant production, which is only these 2 diagrams. Yeah. So the limits they put out are either purely non-resonant or purely resonant. There are no limits for mixed scenarios, and we'll look at some mixed scenarios because they are favored actually by the analysis of the first order electric phase transition. But the limits that they obtain are not really applicable to this case. Yeah. And the existing exclusion bounds, as I will show to you in a moment, are highly questionable. Now, as I told you, there are these 2 BSM physics cases, either kappa lambda is not equal to 1, and we have additional BSM triple Higgs couplings. And I'll show these 2 effects in one plot that we put out recently, where we now look at the quantity that will be analyzed actually at the LHC or high luminosity LHC, and this is the MHH distribution, the invariant mass distribution of the di-Higgs pair. So we look at the 2 Higgses, they decay, and then we add the 4 vectors and we get the invariant mass of the di-Higgs pair. And this is the differential cross-section with respect to this distribution MHH. And well, this is the old plot where we didn't put the standard model line. The standard model line looks like this. It goes up here and then goes smoothly over here. Yeah, this is standard model. And we can now look at the effects of the 2 BSM cases that I want to make. First of all, that the kappa lambda at tree level here, it's close to 1, but at the loop level, it goes up to 3.6. So large effect from the BSM triple Higgs couplings that give us the corrections to this triple Higgs vertex. And the effect is that from this kind of behavior that we see here, we have this behavior now. So we have the peak goes up at very low values of MHH and then goes down and continues over here. The second effect that is important is now the effect coming from the BSM triple Higgs coupling. Yeah, we have this resonant diagram, and exactly at the resonance, we get the famous dip peak structure. This is exactly where the resonance is located. This is the mass of the heavy Higgs boson right here. And we don't go smoothly here anymore, but we have this dip peak structure that comes from the interference of the resonant diagram with the other diagrams. Yeah? This is what one can observe. So coming from the smooth line here, what we would really have in this point is this line here. We first have the first peak, then a kind of shallow minimum, and then a little dip and a high peak, and then it continues here. Yeah? So this is all present if one takes into account the 2 BSM effects that can be relevant in the 2H And I will show you a few more effects, which will be important in the very last part, in the last 5 minutes of my talk. This is one benchmark point, 2HDM type 1, with these masses and these parameters. And let's look at the red line. This is the red line that we've effectively seen before. Just we do not take into account in this plot here the corrections to the kappa lambda. We focus here on the BSM triple Higgs coupling, and then we see this red line, which has this famous dip peak structure. But of course, the fact whether it's dip peak or peak dip depends on the sign. Well, and here we just artificially flip the sign to positive, and then you can see that from this dip peak, we get to a peak dip structure. And when we saw this, we thought, okay, so we have now this heavy Higgs in the resonance. We have this BSM triple Higgs coupling that enters into the game, and depending on the sign, we get a completely different signature here. Maybe it is possible from the measurement of this MHH distribution to get a handle on the value of this parameter here, or at least on the sign, because the sign, as I said, gives you a strong variation. And so this was when we got interested. Maybe the high luminosity LHC will give us access to this BSM triple Higgs coupling, something completely new. Nobody has ever looked at the determination of BSM triple Higgs coupling. Can this be done? But I have to warn you, this is an idealized case because there are experimental uncertainties, and we come to this on the next slide. The determination of MHH is not precise, but it's rather experimentally smeared around the true value with 15%. And if the smearing is applied, the red curve looks like this and the blue like this. Yeah, they're still different, but the difference is much smaller than originally thought. So the question remains, can we have access to this triple Higgs coupling? And this is not the end of the story, because the resolution in MHH is not as fine-grained as I show you here, but it's rather at the level of 50 GeV. So we need a binning of 50 GeV. And if you bin these two, then the red curve and the blue curve look like this. They still look a little bit different, but optically it would be much more complicated to even get the handle on the sign of these BSM triple Higgs coupling. And so then we got a bit disappointed, and we thought we will probably not be able to see something. But in the last 5 minutes that I'll come to in a moment, I'll show you how this might be done with a neural network analysis. This will be the last part of the talk, starting from this kind of distinction for these two cases here. But before I get there, let me make one more case, namely the fact that the experimental results are based on either purely non-resonant or purely resonant Higgs production. And let's focus on the right-hand side here, where we take into account all the effects. The blue curve is, for this parameter point here, the result from the purely resonant diagram. And this is what the experimental collaborations take into account in the analysis. They look for this kind of distribution. And they say, do we find this kind of distribution, or do we not find this distribution? And based on this, they give their exclusion limits. However, for this point here, the real distribution would be the red curve, where we take count all the diagrams, which looks completely different. Yeah, so this is the real distribution. This is what the experimental collaborations take into account. And to make it more clear, this is one point where taking the recasting of the experimental result, the blue curve of this point would lead to an exclusion. Yeah, so this is a parameter point where taking the, I think it's Atlas in this case, result tell us, yes, this point from the resonant Higgs production is excluded, but the real distribution is the red one. And now you tell me whether the red one is sufficiently close to the blue one, whether this point is reliably excluded. And our conclusion is that no, that the exclusion bounds that are put out, if we are in this kind of mixed scenario, then they give a completely unreliable result. And we can't just say whether this point is excluded or not. Yeah? So be aware that if you take Atlas resonant, or also CMS resonant Higgs searches, these results can be not reliable for the particular case that you may be in. Yeah? This is a very concrete example for this. And with this, I come to the last part, which will take only 5 minutes, where I start out with these two curves given by the two different signs of the BSM triple Higgs coupling. And the question is, can we get access to the triple Higgs coupling? And actually, what one can get access to is always the product of the top Yukawa coupling of the heavy Higgs times the triple Higgs coupling. Now, they always enter as a pair in this BSM resonant diagram. Good, this is the starting point. And then what we wanted to know is what we can do is we take a neural network to do this. And to define the playground here, we just took one plane in this cosine beta, tan beta plane. This is the allowed parameter space. All the other parts around are extruded by one or the other constraint that we have. And the color coding tells you the value of the quantity that we want to extract. This is the parameter plane. We find values here between -0.1 and +0.1. The black lines indicate where this product here is 0, either because lambda is 0 or because the Topiokawa coupling is 0. But this is the range that we are interested in. And this is the parameter point that we will analyze in a bit more detail in the plots that I show to you. And here the heavy Higgs mass is set to 450 GeV. And I said this area here is allowed by all theoretical and experimental constraints. Now, this parameter point that I showed to you results in these curves. This is the standard model curve, no resonance. With the resonance, this one here, and including the smearing, the red line. And if you take into account the binning, we get the red line that is shown over here. This is the result. This is the MHH distribution coming from this particular point here. And now we can evaluate the MHH distributions for the whole plane, feed this to a neural network, and then ask whether with this trained neural network we can get a handle on this product. So we have 16 input values depending or given by these 16 bins that we have here, all smeared and binned realistically. We have 4 hidden layers with 120 nodes each. The output layer yields this product here, and the training was always performed with 3/4 of this plane, randomly chosen, and then the result is evaluated for the remaining quarter, very roughly speaking. This is the idea of the neural network. And you can vary these 3/4 and vary this quarter, that in the end you get an idea of the whole plane, what's going on, whether you can determine something. And if you do it like this, the result, this is the theory prediction, and this is the neural network prediction. The result is completely straight. You really you can pin down with the neural network the product of this BSM triple Higgs coupling. This is really remarkable. But of course, this result is fake, because the input that we used was, or the input that we used to determine the triple Higgs coupling, always assumed that the MHH distribution is exactly as given by theory. No statistical uncertainty taken into account. And this is not realistic. This is, again, this distribution. And now these error bars indicate the statistical uncertainty that we would get. So in reality, we would get a curve that is statistically distributed with these uncertainties. And this has to be fed to the neural network to determine whether we can get the product out. If not the mathematically calculated one, but the statistically smeared one can be determined. And if one does this, this line here transforms into this huge blob. And then you get very disappointed. You think, well, you still get a handle on it, but it's not very good anymore. However, this plot here neglects densities. There are many more points located at the diagonal than the sparse points lying out here. If one takes the density of the points into account, one gets to this plot. So now for each bin, we normalized it to 100. You can see that for each bin, actually, in most of the cases, you end up very close to this diagonal line. So it's still not perfect. You have these outliers here and here. But in most of the cases, the neural network would give us a good determination of the BSM triple Higgs coupling. And this all takes into account anticipated experimental efficiencies, etc. If the efficiencies would be better by a factor of 2, which one may hope, because experimentalists always outperform themselves, then this result is obtained. And here we are really very close to the diagonal line, which tells us that, yes, with the neural network, although optically for us impossible, the neural network will be able to determine the BSM triple Higgs coupling quite accurately in this case here. And with this, I conclude. I started out with a question, why is there more matter than antimatter? The answer is electric baryogenesis. This brings us naturally to the first order electric phase transition. This brings us naturally to BSM Higgs sectors. And as a bonus, this may give us gravitational waves detectable at LISA. Our question was, can this happen with 2HDM? What are the implications for the triple Higgs couplings and for the gravitational waves? First of all, we found that the requirement of the first order electric phase transition requires that this kappa lambda is around 2, particularly if we want gravitational waves. and this is bad for the high luminosity LHC, where the determination deteriorates to 70%, but good for the IOC 500, where it improves to 10%. We also had this large mass gap as a good prediction, which gives us the smoking gun signature. There was this axis, which was not confirmed by CMS, which may, if one is lucky, even result in possible gravitational wave detection at LISA. If one looks at the determination of triple Higgs couplings, all the determinations so far, they focus on the case kappa lambda equal to 1. So they don't take into account deviations from 1, and they don't take into account the BSM triple Higgs couplings. And we try to go these 2 steps beyond. I showed you in detail that the searches for the resonant X reduction, the experimental analysis, they leave out the interferences. The results are not reliable. You can't just take them over to your realistic case where we have the mixed contributions as well. And in the last step, I showed you that if one wants to get access to the triple Higgs coupling, one can employ a deep neural network. And this shows a remarkable sensitivity and gives us hope that indeed, if we are in this parameter space, which is favored by the first order trace transition, that we can get a handle on the BSM triple Higgs couplings. Thanks a lot.
Thank you very much, Sven, for the very nice talk. So normally we try to use the raised hand feature for people to ask questions. So sometimes it works, sometimes it doesn't. So if you can try to use if you can try to use that, please raise your hand. If not, you can unmute and just ask. Don't see at the moment any raised hands, so I might just ask a question while people try to get that to work. Actually, just very quickly on the last few slides, you talked about the density of points. I just wanted to, but by density of points, you just mean from the scanning over the parameter space. So it's
so let me go back here. For each point of in the parameter plane, we determined these uncertainties. And then for each point, we threw 5 different randomly assumed MHH distributions. So each point in the plane transformed into 5 points that we actually analyzed with a more realistic set here of this MHH distribution. And this is why, for example, here we see a spread of points always. Yeah, this is not 1 point, because each point we took 5 times randomly distributed. And this is sometimes, if we are unlucky, I don't have the plot, but if we are unlucky, we are just outside the 1 sigma intervals. And then the realistic distribution is very far away from the ideal one. And this results in these outlier points. But this happens only with a low probability. With a higher probability, we find a set where we are within the 1 sigma uncertainties. And then the neural network can still do the job. We end up here close to the diagonal. And this is reflected in the density point, where we took this effect into account.
Okay, very good. Thank you. Let me see. So I have more questions, but yeah, if you want to ask a question, please do raise your hand or interrupt. So I also wanted to just check about about slide 22 or 23, somewhere around there. We had these 2 different diagrams, one of which you include and one of which you don't. And so you're saying
this we do not include.
Yeah, and so the one you include is sometimes the dominant contribution, because this
it can be dominant. Yes,
it depends on the Two Higgs doublet model parameter. And computing the one on the right is not done. It's just because it's technically not been calculated, so it's just a project waiting to happen. Or okay,
I mean, this here it's a product of 2 one-loop diagrams effectively. This is much easier. This is a 2-loop box with many different masses. And so I think it has been done for the standard model, but not for the BSM case. And therefore, it doesn't exist, and we can't include it right now. I hope this can be done, and then we can see how reliable it is. But as I said, what we are doing is at least consistent in the sense that this is always a closed subset. It's not that we have diagrams with the same coupling structure that we leave out. No, those are all taken into account. But of course, if the triple Higgs coupling here is small, then these diagrams are of equal size and would yield a different contribution to the MHH distribution. This is known, but there's nothing we can do about it right now. We hope that some people who are able to do this calculation can do can complete this calculation, that we can actually use it.
I see, and then when you're using it in results, you're clear when it is dominant, when this is dominant, or when it's not.
If we get to a kappa lambda value of 2, which is favored, meaning we have corrections of 100%, and those are only possible if these are the dominant ones. Yeah, so I think in the parameter space where we are okay. Yeah, we get these large values, and then these are dominant ones. The ones with additional top to cover couplings, they usually don't yield corrections of 100% or so. This is only possible by this kind of diagram.
Okay, very good, thanks. I also wanted to ask you about the gravitational wave spectrum. So if you, I don't think you showed the actual fits that you're using and what you're putting into them. So,
sorry, I didn't understand.
So these amplitude curves, you're computing them presumably from some fits to the data. So first of all, you're including turbulence and sound waves.
Well, for each point, let's say for each point in this zone E, in principle, we can do the calculation of this curve here. This we can do, and yeah, we do it for a subset of those. And when we do this calculation, we do this integral, because this curve here is also known, this is fixed, and then we can evaluate the signal to noise ratio. Now, I didn't show you the signal to noise ratio for the whole plane here, because it becomes very small. Only in a small strip close to the vacuum trapping, we find that the signal to noise ratio here is larger than 1, and we can actually see something.
Okay.
Yeah, but for most of the parameter space, the signal to noise ratio is too weak. One could hope that, I mean, this is the only experiment that is approved, but there are other experiments that are planned. Also, I think a Chinese one is in the game, where these curves go deeper. They may be displaced, or they also go deeper, and then they all result in a better signal to noise ratio. So there's hope that the area of parameter space that will be accessible with future experiments is larger. But the only one that is approved, LISA, gives us this curve, and then we are left with a very small part of parameter space that is actually accessible, where this is the larger part. Now let me go back here. This is the larger part where we wouldn't see anything. Yeah, here we have a signal to noise ratio of 10 to the minus 9 or so, and it's far too weak. Only in a very small strip here we would be lucky. But this is, as I said, one of the findings, because originally, let's go back here to this plot, people thought, look here, we have this nice zone where we have these strong first order phase transition, and here we get a large signal to noise ratio. People calculated this, but this zone, if you look at a bit more closer, is disallowed by the phenomenon of vacuum trapping. Yeah, so nature's a bit unkind to us. And the zone where we originally, or where people originally anticipated a large gravitational wave signal, this is where the where actually no phase transition takes place. Yeah, this is what we found in our analysis.
Okay, interesting. But so what I was actually asking though is there's collision contributions to this, and there's turbulence and the sound waves.
Yes.
You include all three, or you include just sound waves, or sound waves and turbulence? I
think we include sound waves and turbulence. Yeah.
Yeah, actually.
And I think collision is subdominant, if I remember correctly. Yeah. And I know, I mean, there are people like you that analyze the reliability of these calculations, and we take the results from the literature, I have to admit. Yeah, we don't do this ourselves. This we take from the literature, because our expertise comes more from the collider side, and then we try to combine these two. And I think one must not underestimate the uncertainties here. The uncertainties in all these calculations are still very large, but I'm convinced that the general effects that we see will persist. Yeah, that in principle one can have gravitational waves, that the gravitational waves are strong only in a small strip. Where this happens in the parameter space, whether it's here or whether a more detailed calculation would move this around somehow, this may well be. But the general effects, I'm convinced that they will persist beyond all the uncertainties that are still into the game. And again, we hope that other people will do better calculations that we then can take over. Yeah, we try to do better calculations, other parts of the analysis, and we hope that the parts that we rely on the literature, that other groups can do the job there.
Okay, great, thanks. So I'm trying to just keep an eye on people raising their hands. I don't see it, but if you're having problems with that feature, please do unmute and just ask a question.
Yeah, I would like to make a comment, but actually I have many questions, but I will try to make like the most relevant ones maybe. So just a quick comment. You mentioned, you very nice talk, really. You started mentioning that one of the ideas for all these projects to make sense is to explain the matter-antimatter asymmetry of the universe. Yes. So you will need some CP violating couplings or sources, but I didn't see that you were using complex Yukawas or complex Scala or complex scalar sector.
Very well observed. Yes, this is absolutely right what you are saying. Very well observed, and we don't actually attempt to calculate the electroweak baryogenesis here. And what we do is we assume that our model is a kind of low energy realization of a model that at higher scales takes care of this, that gives us more impact there. Or additional, for example, complex Yukawa couplings, etc. Yeah, we don't say that the Two Higgs doublet model is the one that explains everything, but we say that there is this one requirement that we can analyze in more detail. Yeah, and this is what we try to do. We don't say that we extend the model to a fully viable model that does all the job. There, I think very few, if maybe one or two attempts of a full calculation here, not even in this model, but in other models where people try to put together all the ingredients. And then actually the calculation of baryogenesis, there are different methods which can differ by an order of magnitude in the results. So there, the uncertainties are even larger, I would say, than in this part of the game that we are looking at. And therefore, we don't claim to do this. We just say if it's a kind of multi-Higgs structure that gives us the first order electric phase transition, which to me sounds very plausible, then these are the other effects that come into the game that can be observed or cannot be observed. Yeah, so we are much less ambitious than your question might hope for.
Yeah. Now it came into my mind because I saw on the slide that Peter mentioned, I think it was a slide 22, on the not inclusion of this second diagram, which is from two boxes diagrams.
Oops.
Yeah, there.
Yes.
So I was looking.
This one.
Yeah. So I was saying that I was looking that the order of the diagram on the left. It's proportional to the top Yukawa coupling, so or to a top light Yukawa coupling. So if that Yukawa coupling is complex, then we could have potential interference effects or something with it.
I mean, we did some analysis on complex Yukawa couplings, and I think the top Yukawa coupling, if it's complex, can do the job provided that the electron Yukawa coupling is smaller. Otherwise, EDMs would kill you. The one Yukawa coupling that can still do the job without tuning the electron Yukawa coupling to 0 is the tau Yukawa coupling. Yeah, this is what we found in our analysis. However, as I was saying, there are two competing methods, and we assumed the optimistic one. If you take the pessimistic one, which gives you the lower baryon asymmetry, then also the tau Yukawa coupling doesn't help you. Yeah, and again, we hope that this will be clarified in literature that we can actually apply this. But you're right, in principle. I mean, here's also a BSM top Yukawa coupling. Yeah, this is this top Yukawa coupling of the heavy Higgs that can also enter here. Also, this has never been analyzed, and I don't know the effects there. Yeah, nobody looked at this. This might be a potential candidate. I agree. For the top Yukawa coupling of the light Higgs, then you have to tune the electron Yukawa coupling to avoid EDM constraints.
Very interesting. Okay, so maybe but my second question, maybe I'm trying to see which one is the more important. Well, this is basic for you probably, but it wasn't clear for me completely why the triple Higgs coupling should be ordered 2 in order to get gravitational waves. I was wondering if there are other parameters that could alleviate this fact, or is it impossible?
This is the result of our parameter scan, where the parameters that we fixed were fixed in a way to already known from the literature, known from previous analyses, that they favor first order electric phase transition. Yeah, and then maybe again the zone E is really found between 1.5 and 2 and a little bit also. Yeah, and only where we are close to the zone D, to the vacuum trapping zone, we get this larger signal to noise ratio. And it's the proximity that we need to this vacuum trapping zone for the gravitational waves that really requires this large kappa lambda. In general, I think in models where we have like 2 Higgs doublets, where we let's go back to this other slide that I showed in the beginning. This one here. We need this barrier. We need this barrier to tunnel through. And there are 2 possibilities to get this barrier. One is that the barrier arises from higher order corrections, from thermal corrections at higher orders or so, which is the case of the 2HDM. Yeah, this is more or less the 2HDM case depicted here. Then we get this, and this naturally implies that the kappa lambda must be 1.5, 2, something like that. The other possibility is that there's a tree-level barrier. Yeah, because you have more parameters in the Higgs sector and the potential that, for example, are forbidden by the Z2 symmetry that we are imposing that can give you a tree-level barrier. And then the situation may be different, that you get kappa lambdas that are not 2-ish, but smaller. But I don't think this has fully been worked out. We are also looking in models right now where we have these tree-level barriers, and we are also evaluating the high order corrections. And we try to get a more general picture of the whole thing. But this is still work in progress. But there are cases indeed that have been worked out where one has the tree-level barrier, not from high order correction, from tree level, and then the kappa lambda can be closer to 1, much closer to 1. Yeah, these are the 2 different cases, depending on the model where you are in.
Okay, thank you. Thank you very much.
Okay, maybe there could be one last quick question. If someone has it, please unmute and ask. You can't use the raise hand thing.
Yeah, hi Sven. I have a question.
Good to hear you.
So,
yes.
Yeah, so you show the 6 thermal history of the Two Higgs Doublet model, and I'm wondering, in your thorough scan of the parameter space, have you found like the 2-step case? And if you find some point that can have 2-step, what's the influence on the later part, like the kappa line?
Yes. So a very interesting question. Cheng is asking about the famous 2-step phase transition, where one first goes, well, here we show one VEF, and then the second VEF starts, and at some point we tunnel through. Yes, the 1-step phase transition. Now, if you have more VEFs in the game, then what can happen is that let's say we have another singlet in the model, and the singlet can have a VEF, and then a third VEF, so to say, can appear, and one first goes to the singlet VEF, and then tunnels through to the doublet VEF, which would be this one here. This is the 2-step phase transition. And in the 2 Higgs doublet model, this is not possible because we have only this effectively, well, we have this V1 and V2, but they always, they go together. One goes from the origin to this new vacuum state in the 2 Higgs doublet model. What you are asking can happen, for example, if one has additional Higgs singlets. And indeed, we also look at the N2HDM, where we augmented the 2HDM by an additional real singlet. And there one can get this 2-step phase transition. But we didn't look into this in more detail. Yeah, this is one of the things I always set in mind to work this out in more detail. For example, to combine it with light Higgs bosons that, we are always interested in Higgs bosons below 125 GeV. This also would naturally probably give you this other VEF where one could tunnel through to, and then one can realize this 2-step phase transition. But indeed, this is one of the mechanisms, if additional singlets are in the game, that can change the whole picture. But in the 2HDM, it's not possible.
So can you elaborate more detail? Why in Two Higgs doublet model we can't have this? I don't quite understand.
I'm not sure how to say it more. It's also difficult to depict the multi-dimensional Higgs potential in an easy way. But I mean, in the multi-dimensional space, we have these 2 distances, from the origin in the 2 dimensions. And one can live, of course, we live in in a kind of combined vacuum of the two, where the sum of the squares must be equal to the standard model VEF square. And what we found is that only this kind of transition can take place. I think the problem is that we can't really picture this multi-dimensional space, how we can live there, how we can tunnel through or not tunnel through. Yeah, I mean, you have a dimension, but then it's also usually, let's say, it's not only one Higgs dimension. It's well, one has to see it. Each Higgs can give a kind of three-dimensional thing, and then it's very complicated to imagine this. But
okay, yeah.
What you have in mind?
Yeah, maybe we can discuss
well, we didn't
more,
find, but I also can't
yeah.
really imagine how it should happen. But maybe this is my limited imagination of this multi-dimensional potential here.
Okay, thanks.
Okay, yeah, maybe we can discuss more about this later. Yeah, thank you.
Yes.
So we do actually have a raised hand from Cheng Li, and since someone, just go ahead.
I thought I thought it was Cheng.
Sven,
the voice it was not your voice, Cheng. Yeah, I thought what happened to his
of
voice.
course. I mean, it's a very impressive talk. Yeah, but I'm also interested on the machine learning technique to determine the BSM Higgs triple hub couplings or something like that. Yeah, I'm wondering if we have like single extension like N2HDM or 2HDMS. So if we have a 95, then is it possible to disentangle so 3 Higgs contributions from here?
Yeah, that's a very good question. Nobody looked at it. This is the short answer. Yeah, we just don't know. This is the first time that it was attempted to use neural networks to determine this BSM physics here. Yeah, and my idea is that once, well, this is close to publication, once this is out, that we expand on this in other models or so. Yeah, having, I mean, here one triple Higgs coupling comes into the game, and this is already, it wasn't easy to do it. If we now have even 2 triple Higgs couplings entering the game, then again you would add another dimension here. It may be possible. I don't know. Yeah, it may be interesting to look at it. I agree, and yeah, but it just hasn't been explored. It's an interesting question, and one should keep an eye on it. I fully agree. Yeah.
Yeah. Okay.
But I mean, we were lucky when we saw this result here. We were happy, and when we saw this result, we were even happier. This was far beyond my original expectations. Yeah, that this might be possible. But going beyond this, you can imagine that also then more uncertainties come into the game and things deteriorate. But yeah, it's a very valid question. I agree.
Yeah, I think for this, it looks promising, right?
Yeah, this looks super promising. Yeah, as I said, it assumes that the efficiencies will be better by a factor of 2 than what the Atlas and CMS are currently claiming what they can do. But I mean, looking at our history, I wouldn't think that this is unrealistic in how they will outperform themselves. Yeah, but this is why we just give this idea of a factor of 2.
Yeah, thank you.
Yeah, sure.
Okay, I think it's 20 minutes past now, so probably we should yeah, we should probably wrap up. But thank you very much for the very nice talk again, Sven.
My pleasure.
If you could send us the slides as well, we'll put them.
Of course, I'll send them
on our
to you.
website.
I'll
Thank
send
you very
them
much. Okay, so thanks again
Good.
for the
Then
talk.
have a
and
great afternoon, and hope to see you soon in 3D at some point. Yeah.
Yes, it would be great to have you over in person sometime. That would be excellent.
Yes.
Okay, take care.
Okay.
Have a good
Bye-bye.
morning.
See you.
Bye.